All right, we'll continue with our study of thermomechanics. If you recall what we did in the last segment or the last couple of segments, we derived the balance of energy for the extended case of thermomechanics, right? And then we wrote out the entropy inequality. And finally, in the very last segment, we talked about the Legendre transformation, which introduces a new thermodynamic potential, the Helmholtz potential. And I believe I also mentioned that it often goes by the name of Helmholtz free energy. Okay, so we're going to pick up from there, and the way we will do that is by first putting down those conditions, right, those equations. So, right, so let's just recall where we were. The first was the balance of energy, the first law. Okay. Right, the first law of thermodynamics. It took on the following form. Okay, on the left-hand side, we have the rate of change of internal energy, and that's the material time derivative. On the right, the very first term is the effect of local heating, where R bar is the heat supply per unit mass, per unit time. The next term is the divergence of the heat flux, and the third term is the internal stress power. It's the rate of work done by the stress on the deformation, right, on the rate of deformation. Okay, so we have this, and then we have the entropy inequality. This is the second law of thermodynamics. And this takes on the form material rate of the entropy per unit mass is greater than or equal to the supply from local heating minus the effect of the heat flux, right, in every little volume, plus a term which takes on the form of the heat flux dotted with the gradient of the temperature. Theta here is the temperature. Okay, so that is the second law. And we note, of course, that it is an inequality. The last thing we introduced was this Legendre transformation, which gives us the Helmholtz potential. Okay, and this gives us the Helmholtz potential. Chi. Okay, and that relation is chi, now written as a function of, I believe I was writing the strain first, so let's just stick with that. Function of the Lagrange strain and the temperature is equal to the internal energy per unit mass, and I realize that I defined chi perhaps without including the bar over it previously. I'll do that now, just to remind ourselves that we are indeed speaking of something of a quantity that's defined per unit mass. So we have E bar, which is a function of the strain and the entropy minus the temperature times the entropy. Okay, this is what we have. And what we're going to do now is proceed from here and try to understand what we can get to from here. The way we are going to do this is by computing first the material time derivative of our Helmholtz potential. Okay, so what we want to say here is that we want to consider rho times material time derivative of chi. That's easy enough to write out from the Legendre transformation. Okay, and the way we would write that out is by saying that, well, we have rho times material time derivative of the internal energy minus rho times material time derivative of the temperature times eta bar minus rho theta material time derivative of eta bar. Okay, and then what I'm going to do is bring this term over to the left hand side. All right. Okay, and when I do that, we get material time derivative of the Helmholtz potential plus rho material time derivative of the temperature times eta bar equals rho times material time derivative of the internal energy minus theta times material time derivative of the entropy. Right. Now, if you go back and look at the form of our first and second law that we put down on the previous slide, okay, and I'm going to do that just briefly, okay, right. If you look at the left-hand sides of the first law and the second law on this slide, okay, that's the first law, that's the second law. You observe that by just multiplying the second law, the statement of the second law by theta, right, and subtracting it from the statement of the first law, we get something that we have on the right-hand side here. Okay, this right-hand side. Okay, so substituting the first law minus the statement of the second law times theta. Okay? If you do this, what do we get? Okay? We get the following. We get rho material time derivative of the Helmholtz potential plus rho, and I'm going to write this as rho eta bar material time derivative of the temperature. Okay. Now, you remember, and this is something that you can look up in your notes, right? The form that we have for these two terms from the first law and second law is slightly different. Okay, for for the material time derivative of E bar, we have an equality. However, for the material time derivative of the entropy, we have an inequality. In particular, we know that the material time derivative of the entropy is greater than or equal to a quantity on the right-hand side. I'll go back once more just to point that out to you. Okay, here we go. We have an equality for the first law, the second law is an inequality. All right. Now, when you combine those two terms and put them, these two relations, and use them on the right-hand side here, and also observe that for the time derivative of the entropy, we are going to flip the sign. We have a minus sign here. Okay. What you will conclude is that that the relation we have here is not an equality, but it is that one. Okay? It's an inequality, and it's a lesser than or equal to. Okay? Right? So what do we get on the right-hand side, though? We get the right-hand sides of the first law and the second law. Okay? From the first law, we get rho r bar minus divergence of Q plus the rate of working of the Cauchy stress. And from the second law, we get the following. We get theta multiplying rho r bar divided by theta minus divergence of Q divided by theta plus Q dot gradient theta divided by theta square. Okay? The reason we have a lesser than or equal to is because of the fact that the entropy relation is an inequality. Okay, and it was greater than or equal to, the minus sign flipped it around to make the whole right-hand side lesser than or the minus sign worked to give us this inequality. Okay? All right, but now you observe that there are certain cancellations that work out, right? Because theta goes through here. What we see is that we get, on the right-hand side, we get that cancels out with that. The divergence cancels out here, okay? And what we are left with then is that rho material time derivative of the Helmholtz potential plus this term is lesser than or equal to the rate of working of the Cauchy stress minus that. Okay? That's where we are. Okay, this is another form of, it's another form of the combination of the first and second laws, and there's just a little more work I want to do here. Before we do this, we could observe one more thing. We can observe that we could write this relation out in a form that isolates the Helmholtz potential on one side. I get a minus sign here. In this form, when we recognize that chi bar is something that we've referred to previously as the Helmholtz free energy, okay, what we are getting here is a relation that is sometimes called the free energy inequality. What it's telling us is that in admissible processes, the free energy cannot increase. Okay, it's always decreasing or stays constant. Okay, so the free energy inequality basically says that the free energy decreases. Or really properly, the free energy is non-increasing. Okay? This is an important principle in physics, and it is often used to talk about the evolution of systems towards equilibrium. Systems are at equilibrium when their free energy is minimum, okay? And this statement tells us that systems tend to evolve to that equilibrium state because their tendency is to never increase their free energy, okay, unless you supply free energy in some form. But if you could take an isolated system, that won't happen. And essentially, systems move towards equilibrium. Okay, so this tells us that systems that are isolated tend toward a state of equilibrium at minimum free energy. Okay, and this is a very powerful guiding principle for all of physics. It comes, as we've observed, from a combination of the first and second laws of thermodynamics, and it explains everything from an object falling under gravity to flows, to the evolution of material systems, to the cooling of the universe, right? Everything. All right. So this is what we have. We won't dwell too much more on this statement and its consequences. Indeed, in some sense, all of non-equilibrium physics is about this. Okay, so this gives rise this relation, and actually the second law are the foundations of, in some sense, of what is called non-equilibrium thermodynamics. Okay, which really talks about systems being far from equilibrium, as in the statement on the first statement on the slide, and talks about how systems evolve toward that equilibrium.